This video is for the second topic this week, and it'll be on magnets, gradients, and the MRI system. This is going to be a relatively short video, and we won't get into too much detail. I just want to show you some images of some magnets, talk about some different magnet types, and talk about very briefly the gradient coils themselves and some other electronic components of the MRI system. So let me start here by talking about superconducting magnets. First of all, what is a superconductor? A superconductor is a conductor of electricity that has zero resistance at a certain temperature. Most superconductors in use today have zero resistance at very, very cold temperatures, down near absolute zero temperature. So around, with respect to MRI, the wires that are superconducting are cooled. Let me move on a little bit here. We can show you that temperature. Very cold, meaning about 4 Kelvin. So remember, absolute zero is 0 Kelvin. And I believe, if I remember right, 0 degrees Celsius is 273 degrees Kelvin. So that just gives you a relative idea of the scale. So what are some of the advantages of a superconducting magnet over other magnets, such as a permanent magnet? So really there are 3 types. I haven't listed them here, but you have a permanent magnet, a resistive magnet, and superconducting magnets. Permanent magnets are always on, but you can't really achieve the same high field strength because the magnet will just become so physically enormous. You just wouldn't be able to physically make a permanent magnet that has a field strength, for example, of 9.4 Tesla. The resistive magnet is not always on, and the point of the resistive magnet is you turn on the magnet when you need it and you turn it off when you don't need it. But in that case, you can't, same thing, you can't make the magnetic field strength very large either, because the coils, the windings that make a resistive magnet have resistance. So when you have resistance, you have heat, and therefore to get a very high field you need a large current, which will generate too much heat. So this is why superconducting magnets are used. Some disadvantages, of course, that you need to continuously bathe the coils that make up the superconducting magnet in liquid helium. And for some magnets that don't recycle the liquid helium, because of course the liquid helium will eventually boil off, they have to be refilled periodically, and that's an expensive situation. Some scanners have what is called a cold head that recycles the boiled off liquid helium, and I'll show you what that is in a couple slides here. So here's one image of a superconducting clinical MRI machine. This is actually a breast specific imaging machine. This is a marketing picture, so you see the bore has this light in it. There is no light in the bore. So what you have here is the woman lays on her stomach. This is where her face goes. This is where her breasts go. And what you see here is this table is not only something that she lays on, but this is also the RF coil. And this coil here, or this bed here, is the transmit. This part of the bed is a transmit RF coil, and the bottom part of the bed is the receive RF coil. Now this whole sled assembly slides into the bore of the magnet, and of course that's when the imaging happens. Now one of the advantages to this setup, by the way, this is Aurora Imaging Technology. I used to work there a couple years ago, and they're right in North Andover. one of the advantages is your head, or the woman's head, is outside of the bore. So if people are claustrophobic, this can reduce that feeling of anxiety if you're inside a closed space, because your head is mostly out of the bore. The woman's head will end up right on the threshold of the entrance of the bore. Now, a lot of magnets are for research only. So although it's hard to get a feel for the size of this magnet relative to the one I just showed you, this one is physically much larger. However, you can see the bore, or the center here, is very small, okay, because this machine is only designed to scan small animals such as mice, rats, maybe a rabbit couldn't fit in there. So what you see in the middle, so this is the bore here. Now you have what are called in this machine, you have gradient coil inserts. So these white discs are different sized gradient coils. So for example, this middle one, I could just, if I unbolt the appropriate bolts, I can slide this gradient coil right out, and then I have a larger gradient coil that I can then use to image maybe a larger animal. Some other components of this magnet that are important are, you see here, I'm pointing to this thing here, this is called a quench pipe. So if this magnet, remember, inside the magnet there's liquid helium to keep it at superconducting temperatures. However, if something goes wrong inside the coils, maybe maybe the liquid helium level gets too low, so that the wires start to heat up just a little bit, minuscule degrees of Kelvin. That can lead to a chain reaction such that the wires all of a sudden will lose their superconductive properties and become resistive. In that case, all the liquid helium will boil off very rapidly, and that's called a quench. And if that happens, all of the gas that's generated, all that helium gas, that needs to be vented somewhere, and it's vented out the quench pipe. Now, this is an important thing, because if it's not vented, the gas can fill up the room, and therefore if somebody's in the room, the amount of oxygen will go down to a life-threatening level. So the liquid helium gas, in the event of a quench, needs to be routed out through this quench pipe. And what else you see here these are the cold heads. So if you're standing in this room next to the magnet, you're going to hear this whistle, kind of this on-off sound, squeak, 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 squeak type of sound. And that's this cold head going on and off. And it's kind of like a refrigeration cycle, where it gathers the tiny amount of liquid helium that boils off naturally, and it recycles it through these tubes here. It goes back to what's called a heat exchanger in a different room, and then it returns the liquid helium to the tank. So theoretically, this system will never lose helium as long as the cold heads are operating. So I think that's about it for this type of magnet. So let's look at some of the internals. So again, I mentioned the cold head. I don't think this particular diagram shows a cold head. It just shows a tower where you can fill the helium. And in this particular design, there's an area here for helium, and there's an area also for liquid nitrogen. So some magnets have layers of different cold liquids. Some older magnets, if they don't have that cold head, they'll have a layer of liquid nitrogen and then a layer of liquid helium. And the point of that is the liquid nitrogen helps keep the liquid helium intact longer. But for a magnet like this, a design like this that does not have a cold head, you will have liquid helium boil off, and therefore you'll have to keep filling the helium about every 3 months or so. Liquid nitrogen you need to fill it about every 2 or 3 weeks. So it is labor intensive. I've also done a little bit of an animation here, so you can see this is how the person would fit in the magnet. patient bed here. And now we're inside this region. And of course the sled would slide in. Most clinical machines, the sleds automatically slide in to a position where the technologist can enter on a keypad, say go in by 35 centimeters or half a meter or whichever it happens to be. So inside, so now let's talk a little bit about gradient coils. I only have a couple slides on this because this is we can get really involved in this, but I just want to show you what they look like. This is a image I borrowed from the internet. I'm sure you could probably find it if you Googled it. So the point is to show the former. So this kind of this gray circle is usually what people call as the former. It's the physical cylinder that the coils use for mechanical stability. And the coils here, you can see the Z coil are these two discs. So these two discs combined make the Z gradient, or the gradient in the magnetic field in the Z direction. Now the X and the Y coils are identically shaped. So the X coils are in red, the Y coils are in blue. So they're identically shaped, but they're just shifted in position relative to one another. So of course you see B0 is down the center. If we look at here, and I scanned in a picture from a really old MRI book that I have, and I thought it was kind of neat because you can there's a picture of these being built. So you can see here the former, and it's really kind of neat watching one of these made. You picture I'm not sure if you've ever seen a milling machine, but or actually a lathe. These large cylinders are made of fiberglass, and they're placed on gigantic lathes. So they spin around, of course, to make them perfectly, or as perfectly cylindrical as possible. And after that, the coils are wrapped around. You can see the wire here. And in this case, what they've done is they've added a layer of some kind of material to absorb the force that's going to occur when these coils are excited. So that'll dampen the vibration that the coil will undergo during a pulse sequence. This next image shows, I don't really know what all this stuff is in here, but and again, I just wanted to show you some of the internals. So here, again, the Z coils, and I believe this is the Y gradient coil set. So again, all of these coils I'm pointing at right now, hopefully you can see my cursor right now, all the coils here make the Y gradient. These two coils together make the Z gradient, and maybe in here is the X gradient coils. So let's just look at one image of a functional block diagram. I borrowed this from Joseph Horneck's website. Now, so here he's showing the shield. So what is the shield? This is basically, this is not to scale. So the room that the MRI machine is in, the actual magnet is in, is surrounded by a layer of copper. So you don't walk into an MRI room and you look at the walls and see copper, but behind the sheetrock is copper everywhere, on the walls, on the ceiling, on the floor, and that's called a Faraday cage because it prevents electromagnetic energy from getting into the room or exiting the room. Okay, so you don't want, for example, maybe a harmonic of a TV station, because let's say if we're at 3 Tesla, then we're at 128 megahertz. And think about some radio stations. KISS 108 is at 108 megahertz. So maybe you can get something from a TV, or an FM radio station, if it was strong enough, could leak into the room. But with the shield there, you will not get any RF into the room, because you don't want any RF in the room being picked up by the RF coil, because if it gets picked up by the RF coil, that signal will look like an artifact in your image. So he's showing here the magnet, of course, the gradient coils. He also shows the RF coil. So I know as you remember, we talked about the RF coil in the last topic. Some machines have a built-in RF coil, so right in the bore. So this is called a body coil. While the coils then that you would place, for example, around the brain here would be a receive coil. Some machines don't have this built-in RF coil, but I believe most newer clinical machines do. So what else do we have down here? So in a different room, you would have these components, the gradient amp. Actually, there are 3 of these, one for X, one for Y, and one for Z. And let's see, does he show the RF amplifier? Yes. So in the other room, you would typically have cabinets, and the other room being an electronics room. And each cabinet would have a rack of gradient amplifiers, a rack where the RF amplifier resides, and also a rack that includes a shim power supply. He does not show the shim coils in here. The shim coils would be located right about at this level. So of course we need a power supply to power those coils, and remember with the shim, the point of the shim is to make the magnetic field, the main magnetic field B0, as uniform as possible. The computer, all these other components, the RF detector, digitizer, pulse program, and RF source are located also in their own rack. And these guys here that I'm circling now, also with this one, usually make up what's called the spectrometer, or the brains of the scanner. The computer is just, it can be either your standard desktop PC, maybe a Linux PC that the operator is actually using. Film, that's an old reference to when the MRI pictures were actually printed out on a film, like an X-ray film. Now everything is digital. All images are now in DICOM format, DICOM. So DICOM. So everything is in DICOM format. Now it's a standardized way of looking at images. So it's not only for MRI, DICOM applies to all the other imaging modalities, X-ray, PET scans, and so on. Okay, so that's just a really quick look at the system block diagram. And that's really it. So if you want more information on any of the stuff that we've talked about throughout the course, I highly suggest you check this website out. It's very useful, has a lot of interesting links, educational links, informational links. It talks about conferences. There's a yearly conference at different cities throughout the world. So yeah, if you want to continue with MRI, I suggest you go to the site. Okay, thank you.